Now let's have a little bit more of a detailed look at the cranial nerves. We'll start off with cranial nerve number 1, which is the olfactory nerve. We can see here that this little part is called the olfactory bulb. It will sit in the cribriform plate, where actually the olfactory neurons extend their little axons through the holes in the cribriform plate. It's like a sieve, and they reach the olfactory mucosa, where then they can detect odorants. Okay, so it's a special sensory nerve for the sense of olfaction, smell. Right next to it here is the crista galli. Then we have the olfactory tract, which is leading backwards or is afferent towards the brain. And here is, here we can see a little bit of the cribriform plate and parts of the olfactory nerve axons passing through these little holes in the cribriform plate. If we were to magnify this and have a close-up view of the olfactory mucosa, we would be able to see that the olfactory receptor neurons are actually bipolar cells. So their dendrites will show kind of bulbous expansions with pretty fine cilia, and the cilia are then bathed in a layer of mucus, which is secreted by the olfactory glands in the mucosa. To be able to smell, we actually have to be able to dissolve odorants, so those are these smelly molecules, in a fluid layer which is in the olfactory mucosa. Putting together all the axons of these bipolar olfactory neurons, that constitutes the olfactory nerve, and they will leave the nasal cavity via the cribriform plate of the ethmoid bone to enter the olfactory bulbs of the brain. The synapses will then occur with cells which are called mitral cells in the olfactory bulb, and the axons of these mitral cells will then constitute the olfactory tract. As you can see here, it is going towards the brain. Thus, the olfactory receptor neurons act both as receptors but also as conductors. For the other special senses, the receptor cells that receive the stimulus don't directly conduct the stimulus back to the brain. In humans, we have about 25 million olfactory receptor neurons, and that is in each half of the nasal cavity. Also interesting about this is that these cells are actually continuously produced by mitosis, and they're continuously lost through desquamation. In the healthy human nose, each neuron lives for about 3 months. However, our sense of smell is not always going to be as keen as we would like to have it. With aging, just like most of our bodily functions slowly deteriorate, well, it has been shown that there is on average a loss of about 1% of neurons per year of postnatal life, which is probably one of the reasons why older people usually have a reduced sense of smell. So the chief complaint of people that have anosmia, which is the loss of smell, is the loss or alteration of taste, because, well, food flavors depend on the sense of smell and not on the sense of taste. You might know that from your personal experience. If you have a severe cold, you can't breathe through your nose, you're all stuffy, usually things do not really taste that good. In animals that rely greatly on their sense of smell, for instance for hunting or for tracking, the amount of olfactory neurons is much, much higher.